Hi folks, welcome to this lesson on area in the plane. So area between two curves over some interval from, let's say, from A to B. So here's A and here's B. We're talking about area, so that means it's going to be a positive number. So I'm going to fill in this area in red. It doesn't actually matter whether we cross the x-axis. It can be given by a really elegant little formula. The area is going to be the integral from A to B, you probably saw that one coming, of f of x minus g of x dx. And the f of x has to be the top curve, and the g of x has to be the bottom curve. And if they switch roles, well, that's going to cause us some issues that we'll get into in one of the examples. Having a sketch helps you know which one's on top. So if you end up with an area that is negative at the end, then you've probably botched which one's on top. Here's the way that I think of it. I think of it as area is the integral from the left bound to the right bound of the top function minus the bottom function. And if I keep that straight in my head, then typically these questions go well. Now, there are a bunch of sort of subtypes, just depending on whether you know the actual boundaries or you have to find them, whether we're talking about area between the x-axis or the area between two other functions. So we'll go through some examples in the next two videos of sort of progressively more complicated questions. All of it will boil down to, though, this idea that area is the integral from left to right of the top minus bottom. The thing that is going to make all this easier is, whenever possible, draw a rough sketch. It doesn't have to be an amazing sketch, but you want to figure out what's on top and what's on bottom. Okay, here comes our first one. Area bounded by y equals x plus 4 and y equals negative x minus 2. Those are two functions, and these are the vertical lines that are going to be the boundary. So x equals is a constant. It is always going to be a vertical line. And let's draw these other functions. So maybe I'll do this one in blue. 1, 2, 3, 4. It has a positive slope, and it's y equals x plus 4. And the other one, maybe I'll do it in red. It has a negative slope and a negative y-intercept. So, I guess it looks something like this. Again, I'm not too concerned about how perfect my sketch is. And then this area is bounded by x is 2, and x is negative 1. So what I'm looking for, I'm going to do the area in my favorite color of purple. I'm looking for this area right here. And so I set it up. Area is the integral from the left boundary, which would be negative 1, to the right boundary, which is 2, of the top function, which would be in blue. So I'm going to use a bunch of brackets here just to be sure. Top function minus the bottom function, which is negative x minus 2 dx. Before I go ahead and anti-differentiate, I think I want to simplify this. So this is x plus 4 plus x plus 2 dx. Or I've got 2x plus 6 dx. Now I'm feeling confident I can anti-differentiate that. So that's going to give me x squared plus 6x. And I'm going to sub in. So here is sort of my antiderivative. Maybe I won't use f because I've already sort of defined f as something else. So we evaluate this antiderivative at 2. So that would be 2 squared plus 6 times 2. Minus the antiderivative evaluated at negative 1. That would be negative 1 squared plus 6 times negative 1. Okay. And it'll work within the brackets. So in that first bracket, I'd have 4 plus 12, or 16. In the other bracket, I would have 1 minus 6, so that's negative 5. Put it all together, allegedly 21 units squared. I can get the calculator to do something similar. I think I probably want to do it without seeing the graph, so I'll just set it up here. Actually, maybe we will look at the graph. So here's the graph of those two functions, just like I thought. Blue one's going up, red one's going down. I'm going to press second mode to quit. I'm going to press math for the definite integral down here. And I'll give it its boundaries, -1 to 2. And I'm going to tell it by hitting alpha trace that it's just curve y1 minus curve y2. And I have my dx, and it gives me that answer of 21. The nice thing about using it from stored stuff in y1 and y2 is that you don't have to worry about extra brackets and subtraction. You just have these sort of entered as functions that you can play with. So 21 is correct. We used the integral of left to right, top minus bottom. Let's try another. So here's one where they don't tell us the boundaries. And we want to know what's going on with 3x squared minus 12, which is a parabola that opens upward with its vertex at 0, -12, and the x-axis. Okay. Now the x-axis, just to be clear here, the x-axis has an equation of y equals 0. That's what that is as a function. So I'm looking for, again, this kind of area. And to do that, I need to figure out where these x-intercepts are. So if you're hunting down x-intercepts, you sub 0 for y. So 0 equals 3x squared minus 12. You can solve this a variety of ways. I'm just going to bring the 12 over. I'm going to divide by 3. And I know that tells me that I've got x is plus or minus 2. So here's one x-intercept, here's the other x-intercept. Now we're ready to go. The area is the left boundary to the right of the top. Now in this case, the top curve is actually the x-axis. So the top curve is 0. Okay, y equals 0. Minus the bottom curve. Okay, so for us, the bottom curve here is going to be this parabola. If it's a parabola opening up, there's a good chance that it will be the bottom curve. 3x squared minus 12. Are there other ways you could work this through? Sure, but I like this axiomatic approach of left to right, top minus bottom. So let's work this out before anti-differentiating. We've got -3x squared plus 12 dx. And now I can anti-differentiate. And when I look at that -3x squared, I can do it by inspection. That's just going to be -x cubed, and this will be 12x. But if you want to use rules to get there, that's great as well. And now I'm going to carefully sub in. Okay, so I'll sub in 2. And whenever we're subbing in, we should be putting stuff in brackets. 12 times 2. Okay, there's big F at 2 minus -2 cubed plus 12 times -2. And that's going to give us -8 plus 24 minus +8 minus 24. Or 16 minus -16. Area should be 32 units squared. And we can check that using the GDC if we want to. There are my two functions. I can look at them. I can set up a definite integral from -2 all the way to 2 of the top one, which I think I put in as y1, minus alpha trace for y2. We get 32. Wonderful. Okay. You could also have found it by some other methods, but I think this is pretty nice. Notice that if you had just found the integral from -2 to 2 on this, it would have given you a negative answer. which you could have then fixed up and turned positive because you know it's supposed to be area. But again, this technique of left to right, top minus bottom, works every time. We might also be asked to find a boundary. So here's y equals root x. And we know over the interval 1 to m, the area here is 5. We've already done ones that are similar to this before. So that means that we can set up one of these area statements. So on the top, we've got root x. On the bottom, we've got y equals 0. That's what's bounding this curve. So we've got from 1 to m of top, which is root x, minus bottom, which is the function y equals 0, dx. So that's going to be the integral from 1 to m of x to the half dx. And we can anti-differentiate. So power goes up by 1. Flip of the new power goes in front from 1 to m. And sub in. So that'll be 2/3 m to the 3 over 2 minus 2/3 1 to the 3 over 2. And what we know is that this area here is 5. So that gives us 2/3 m to the 3 over 2 minus 2/3. 1 to the 3 over 2 is just 1. I hate these fractions, so I'm going to times both sides by 3. I think that will make my life easier. And at this point, it's just kind of algebraic stuff. So I think I'm going to need more space. So I'll move over here. I'll go 2m to the 3 over 2 minus 2. And if this is a GDC question, then at any point, you could just go to your GDC. And I can divide by 2, so 17 over 2, or 8.5, is m to the 3 over 2. And what can I do? I want to get m on its own, so let's square both sides. So I'll get 8.5 squared here equals m cubed. And finally, m is the cube root of 8.5 squared. I think if we were going to use our GDC, we probably might as well have used it earlier on to solve this graphically, maybe find that m value. But let's check it out as a decimal approximation. Cube root of 8.5 squared. There we go. Let's check it out. Is it going to work? If I take the integral from 1 to 4.16 on root x, am I going to get 5? Pretty much. A little bit of rounding error. To 3 sig figs, 4.16 is a great answer. If I wanted an exact value, well, cube root of 8.5 squared would be lovely as well. That brings us to the last type that we're going to do in this video, which is an area that's bounded by two curves. So this is one where we have to figure out which one's on top, but we also have to figure out where they meet. What's going to be the area that we're caring about? So y equals x plus 1 is a function that looks like this. Y equals negative x squared plus 1 is a function that looks like this. And what is the area bounded by these curves? It's this little chunk here. So I already know here that this is my top curve, and I know this is my bottom curve. What I don't know is exactly where they meet. Now, maybe you have some insight in that. But as a general technique, if you want to find points of intersections, you equate the functions. So find intersections. I'll say x plus 1 equals negative x squared plus 1. And I can rearrange that. I'll bring the x squared over to the left side. I'll have plus x, and the 1's will turn into 0. And then I'll probably factor. So I'll get x by x plus 1. The the points of intersection rather are at 0 and -1. So right here, this is happening at -1, and this makes sense that this is at 0. Now we're ready to find an area. So it's from the left to the right of the top, which is -x squared plus 1, minus the bottom, which is x plus 1, dx. And we'll simplify this a little bit. So that'll give us -x squared minus x dx. We can anti-differentiate. That's -1/3 x cubed minus 1/2 x squared from -1 to 1. And now I'm going to carefully sub in. Now it's a gift here. We've got a polynomial with no constant term at 0. So that'll just turn into 0. So -1/3, 0 cubed, minus 1/2, 0 squared. The other one, we had better be careful. Look at all these negatives. Good grief. So -1 cubed minus 1/2, -1 squared. Okay, that first big bracket just turns into 0. The next one, we'll have negative times a negative cube. That'll be a positive, so 1/3 minus 1/2. So essentially we have -1/3 plus 1/2, common denominator, -2/6 plus 3/6. That area is very small, just like we expected, and it is 1/6 units squared. We can check this all out on our GDC, but it should work out for us. Let's recap. For basic areas, we're looking at the integral from the left to the right of the top function minus the bottom function. If we need to find those boundaries, we may need to find an x-intercept or a point of intersection between the two functions. Here are some questions that go along with those, and we'll do a second video on area in the plane to look at some sort of more complicated situations. I hope this has been helpful. Good luck with the material, folks, and take care.